सामने कैसे स्टार्ट करता
Winter is almost gone, right? Almost, not gone, but almost gone. There's hope that will be warmer days. So for the people, most people like that. People who like skiing and stuff, they probably disappointed that warm days are coming. Few logistics. There's a week of a break, right? Next week we don't have classes, is that correct? Right. We'll have some office hours. So next week, spring break. No classes. Is that good or bad? But some office hours. I probably will have 2 days. So out of the normal evening, maybe Tuesday, Thursday, or something like that. You should check with the TA or Piazza to make sure what those office hours are. My plan, if possible, is for you guys to figure out the current homework, that is homework 4, before the spring break is over. And then after the spring break, you can still demo it. You can come to the TAs and say, here's what I have, done.
Homework 4 says it's due March 1st, which is Tuesday, March 1st, but March 1st is a Friday.
Friday, March 1st. What I really mean is that you should have it done by the end of the spring break, which is March 9th, really. So after the spring break, I don't want to go back and forth with homework 4. You can still demo it, you can come to office hours and show what you have and get a grade. But I don't want more questions, fix this, fix that, come back, because after the spring break, we really need to move on into other more interesting things. We are at that point in the term where we've done the basics, okay? At this point, you should say, I know the machine learning basics. I understand supervised classification, I understand decision trees, I understand basic generative functions, likelihood optimization, regression, some regularization of it. So that's the basic machine learning and neural networks, right? And now we're gonna do some, we can keep going with different algorithms, but there are many, many algorithms. I think it's more important to keep going a more interesting machine learning, which is not the simple stuff. So that's what we're gonna start today. And there'll be, of course, a homework about this. So that's next week. This Thursday is 2/28. I can't make the office hours. So no Virgil at office hours. But I can do Wednesday instead. So everybody wants to see me. The office hours will happen. Normally TAs will be there as normal, but me, I won't be on Thursday. I'll be there tomorrow. We can even do the math thing tomorrow. If people want to talk more about math, we can hang out at night to talk about math. And there was another thing that I think I forgot. You guys missing some grades for the math problems? I'll take the spring break to grade your math problems. Yes?
So the office hours with the TAs is going to be Tuesday and Thursday?
That's during the spring break, not this week. This week is normal.
This week's normal, and then spring
I
break.
don't know exactly the days. I have to talk to them. They are people too. They need a vacation too. Yes. So they, if they want to do Monday, Wednesday, or Monday, Friday, that's going to be up to them. Yes. Normally we shouldn't have office hours. Ketchen may not be available. For Ketchen, if you need him, you should probably ask him by email, when can I see you, or here's my problem. But the other two TAs, I'll probably have them come twice. So you guys can still go back and forth with homework 4. By the way, how hard is homework 4? It's long? The problems are long too, long reading.
Yeah.
But not that hard. Naive Bayes, who made it work? Okay?
What accuracy are you expected to get?
I'm not sure. The TAs.
Is it normal for the 9-bit histogram to have lower accuracy than 4-bit circularly?
Not normal, of course. The problem is estimation, right? You have enough data to estimate 9 bins. If you have enough data, the more bins, the better. It's like generalization issue, right? The more you see training data, the same like testing, the better it's gonna be. But if you fit everything into 90 bins or 900 bins, and then whatever you learn there is not reliable enough, you're not gonna work well for the future point. So all these problems with naive Bayes, I honestly don't care much about accuracy as long as you are in the ballpark. I'll tell the TAs to be relaxed about accuracy. I care much more about you playing with 9 bins versus 4 bins versus 3 bins versus there's a Gaussian form there that you can do instead of binning. Is that right? How about try to fit other things instead than Gaussians? Like instead of chopping the thing into 4 bins uniform, is there a way to do it non-uniform, to say, okay, if you want 5 bins or 4 bins, maybe the bins should be more like this. Maybe my data for feature age or for feature salary or whatever it is doesn't make sense to bucketize it into uniform buckets, because it turns out more salaries are here and here, so I don't, if I do uniform buckets, I get a very unskewed data distribution in there. But maybe by bucketizing somehow by the data, I get better buckets. I'm just asking, is there a better way to do those buckets just this uniform, whether it's 4 or 9, than that? So I'm more interested in you playing with the thing to see where you get rather than the exact performance. Yes?
Could you use a decision tree on one feature?
A what?
A decision tree on one feature and then convert all of its splits into where the bins start and end?
That's not for the grade. I mean, you can try, I would appreciate if you try things like this for naive Bayes. If once you try a decision tree, that's already a power tool. So I
Or
think
just-
it's
just
okay to
figure
do
out the
some
splits.
processing in advance based on variance to say, okay, where my data is. But once you use a learning method like a decision tree, that's already, you know. Yes, other things. Yes.
Just out of curiosity, in practice, do you decide upfront typically how you're going to estimate the priors? Like which distributions or how you're going to do the
There's a
things?
lot of domain knowledge that goes into that.
Okay.
There's a lot of trial and error. There's some measurements too, like basic mean and variance, just to estimate. We have 1 hill, 2 hills, we talked about this last time.
Okay.
Okay. So that being said, let's move to interesting things. Oh, before I move to interesting things, I want to pose 2 math problems. And let's see how fast you solve them. Maybe somebody will solve them by the end of the lecture. Maybe not. So one problem that I have to pose here, it's a very simple problem. Some of you might have seen it, but I want a clean proof. As not in like, okay, let's assume something that's a heavy canon, and based on that, we get it done, like actual proof. So the one that I'm looking at is 1 plus x is smaller than e at x for any x real number. Is that true? I'm sure most of you have seen these things, but how do you prove? Right? Again, not assuming heavy stuff. We'll get to it at the end of lecture. I don't want to give you a clean proof, but I want to give you an idea. And I'm sure some of the math talented people might figure this out like full swing. But again, I know it can be done with existing inequalities and integrals and other things that are more powerful than this inequality. But if I just want to prove clearly this inequality with CS 1800 basic math and nothing else, can I do that? Okay, so that's one problem. And the other problem that I have here, which is, so to speak, the beginning of the lecture. I want to prove something like, I'm not sure what mathematically, but something like the square error in general is, what is it? Is a sum over all data points xi, right? Is a sum between the truth yi minus prediction of xi squared, right? But that's usually the square loss. So that's the truth, right? Prediction. And what I would like to do mathematically is to decompose this quantity, this whole thing, to say that is equal with. So you guys have to figure out what this actually means mathematically. Noise square, three components I have here. Bias square and variance. So that's problem number 2. The reason I say this is a math problem is that I'm not interested in how we produce these predictions. Machine learning gives us algorithm and methods to produce the prediction, right? Like a decision tree or an naive Bayes or a neural network, whatever. In here, prediction is just a function, any function. Doesn't matter if I learn it through a machine learning algorithm or somebody just give it to me. Here's your function, right? So prediction is any function. So it simply produces an output like the y. And then for any function, I can measure the square loss. I can say how good that function is, how close is to the target y, whatever that target was, right? So I'm not interested in here in how people produce the prediction function, the fact that it's a regression. I'm just saying for any function, I would like to decompose it into 3 quantities. I want to give you a little bit more hints about what those quantities are. This is the relation between x and y, features versus label, is not deterministic. Sometimes there is noise. Noise comes from many reasons. It's nothing to do with machine learning. Sometimes the same patient gets 2 diagnoses. They go to 2 different hospitals. They tell they have 2 different diseases. That happened to you? In the United States, it's not so frequent, but in other countries, it's quite frequent. You go to 3 doctors, you get 3 different diagnoses, right? And then when you learn from this data, you're like, okay, which one is it? The ground truth, right? Some people annotate images with different labels. Some people miss an annotation. You ask somebody, okay, label all the tags for this image. They miss 2 tags. That happens all the time. So there's reason that data may not be perfectly learnable. As in, there's some relationship between x and y. Obviously, the target, the truth, depends on the features, but it's not always a one-to-one. So far, we assume this is always perfect, right? The label is always can be somehow computed. There's a ground truth function that gives that y, but sometimes in reality, it's not possible to get to 100%, no matter how fancy the learning algorithm is. It's just not perfectly learnable. So this noise quantity, there's nothing we can do about it. It's like a upper bound on predictions quality. This is not something we can change. That's in the data. And if the noise is 25%, we can say informally the best classification performance that any algorithm can get is probably like 25, 75%, 25% better, because there's no way to get better than that. After that, it's just random, right? So the trivial example to clarify this is that if I flip a coin randomly and I'm asking you to make predictions about what's going to come, no matter how good you are at making predictions, you're going to have a 50% error. Because no matter how you make predictions, any particular prediction will be half on, half off. Data is not like this. Data is not completely random, but there is some randomness. This is performance. This is what we usually measure. How good is my algorithm? Performance of this function I have, prediction of x. How good is that? So this is what, when you train a machine learning algorithm, you typically decrease the bias. You try to match the predictions to be the target. And this has to do with the sample data in training. Like sometimes we don't have a big training set, sometimes we have a bias training set, we only have patients from MGH, but it turns out those patients at MGH are a little biased. They don't have a full representation of all the patients. We only got images from Flickr, and those images have a certain property that does not apply to all the images. So in many ways, unless you have a huge data set, unless you are Google or Amazon, all the data samples you have, they might have been a little biased. Like for example, the DGIS data set, some of you looked at it, maybe all the images that were hard to classify. So there's not really representing all the images that USPS have seen as zip codes, right? So typically, I would like somebody to prove this. How do I write variance, bias, and noise in a way that I can mathematically prove this formula? That the difference we keep measuring, this is the MSE, right? That's mean square error, but mean is just taking 1 over n in front of it, so some square error. Can be decomposed into some square error that's nothing I can do about, data's noisy, some performance of my algorithm, and something to do with how much data I have and how well that represents the true data, right? If I have a small data set, I'll have a larger variance, right? If I take, like the wine data set has 200 examples. Imagine the wine data set having 20,000 examples, there will be a lot less variance in there. Variance has to do with I'm learning what's in my training set. And if the training set is small, there is a chance that I'm not learning exactly the right thing. So I won't talk about this equation until next time, on Thursday again. But this is where we want to look at this and say, in order to optimize a machine learning algorithm, there's really two things that I can do. I can improve the bias, that is the raw performance, that is on the training set, how well that does. How well does it match, right? Because we measure the training error, that is prediction minus truth on the training set. Or I can figure out something about the variance of the estimator. If you know statistics, you know that everything that's an estimator has a variance due to what data you use. So those are my two problems that I would like to solve, say by next week, next Thursday, 2 days from now. And I'm going to come back to this on Thursday to talk about what to do about the variance. For now, I'm going to worry what to do about the bias. So what I'm planning to do is to say, suppose I have H, it's a predictor. I'm going to call it weak predictor or weak algorithm, ML algorithm. Weak, I mean, it doesn't have a high performance. So weak means maybe 60% accurate or 75% accurate or something like that. Something that's not in the 90% range that we're looking for. Like when we train a regressor or a naive Bayes or something in production, we expect a high accuracy. Not all the time, but this, it's weak, but it's simple. So I should write it in capital letters, simple. So for example, one split decision tree. Right? Literally start at the root, choose one feature with one threshold, remember decision trees? Say, do your split once, that's it, done. These are terminal nodes. So you get to pick one feature and one threshold, you split once, and then that's it, you can't split anymore. You predict majority or the average, whatever it is in there, like regular decision trees, right? So this is a very simple machine learning algorithm, right? It just does one split based on one feature, and that's what it is. You can't expect high accuracy on the thing, right? If you do one split, remember homework 1? You probably don't get high accuracy after the first split, but you can expect better than random because you did one split, so maybe 60% is a reasonable estimate, right? So I have access to those classifiers. They're simple, they're interpretable, they're easy to train, easy to understand, all the nice things, except they don't have a high accuracy. And it doesn't have to be a decision tree. Maybe there are many simple algorithms that one can choose that work that way. How do I, obviously, what's the problem with this algorithm in here? where it's gonna suffer. My error is gonna come from where?
Bias.
The bias. It's gonna have a large bias, right? Because it doesn't match very well the prediction with why. Again, noise, it's a constant, whatever it is, I can't do anything about it. The problem with this kind of thing, it's gonna typically have a high bias. I didn't say what bias is mathematically, but bias is on average how far away my accuracy, my prediction is from the truth. That's exactly the error. So the question is, can I use a bunch of these weak learners or weak predictors to improve the bias? Of course, I can make this one more complicated, right? We've seen in homework 1, if I keep splitting, I get better machine learning performance, right? Instead of 1 split, I have 2 splits, 3 splits, 7 splits. And I'm saying, no. I would like to combine them in a different way than just expanding. So you can imagine the expansion, the decision tree, regular decision tree, it means continue the expansion, right? That's what the regular decision tree does. Right? That's what the decision tree will do. Keep expanding the thing until. So I don't want to do that. If I do that, what's going to happen to my bias? When you train your decision tree, how deep did you go? 5 level, 6 level, 8 level, something like that? And what happened to the bias? It decreased. But what happened to the variance? So what's the problem with the decision tree going down? Overfitting. You need a lot more data to not overfit, right? If you go down, you get all these cells, which are, unless you have a lot of data on every single cell, you start memorizing effectively what happened in that cell, and that's not applicable typically for a different data point like in a test set. Now, overfitting is not always a bad thing. Sometimes your test data or production data look exactly like the trained data, right? Sometimes I know that most patients are the same, so if I know exactly one patient, and I count on the fact that my future patients will look like this, overfitting this particular one in training set is okay, because I'm going to have exactly the same patient to predict on, or email. The problem with overfitting is, as soon as my data in production or in testing changes a little bit, is not identical with the one I have, or very, very close, my model cannot make a good prediction. But overfitting is not a bad thing if you know, hey, the data that I'm going to have is going to be pretty much the same like this data. However, if that's the case, there are better algorithms than this. If you know that your future data points or test points are identical with the ones you've seen already, then you probably don't want to train decision tree or regression. You can do something else, like a nearest neighbor sort of thing. Like ask, what's my closest point to that one? Predict exactly that, if you have that belief in the data. Anyway, so this tree will improve the bias, certainly, but will have a problem with variance because it splits into too many cells, and usually I don't have enough data on all the cells to guarantee generalization. So instead of doing this, which we did in homework 1, what can we do? How can we improve the bias, but at least not damage the variance? The low variance in here comes from the simplicity. Simplicity, low variance. Right? I can't really overfit a particular data in training if I only do one split. Simple things cannot overfit. Regression is good that way. I mean, it depends on how many dimensions you have, but the fact that it's a line and it's not a curve or anything else, a line is by definition a simple thing. So it usually doesn't overfit so bad. I have low variance. I would like to keep the low variance or even improve it, but also improve the bias. Yes?
Have multiple simple things and aggregate the results.
Right. That's the idea. So I'm going to try to add more trees this way. Again, they're all simple. I'm not complicating the trees, but by adding them up. And I'm hoping that by adding them up, I'm going to improve both the bias and the variance. or the bias is the accuracy. We can, this is accuracy, right? And this is overfitting. Overfit a particular data training set, that if I have a different training set, I'd overfit in a different way. So the more I'm specific about the training set, the more is the danger I'm going to overfit in. Now, this might seem like a natural thing to think of today in, what is it, February 2019? But the world has been very, very convinced that this is not possible for quite a few years. And I'm talking about extremely smart people. There was a general consensus up to 1995. So when machine learning started looking into more theory stuff, from about 85 to 95, there were 10 years, so a lot of people start studying theoretical. What theoretical properties can we prove about regression, about trees, about neural networks? Like, how do we think of them theoretically, not just running on data? And at the end of those 10 years, most people, top researchers in the field, believe that something like this is not possible. You cannot add simple things and hope to maintain a low variance or low overfitting strategy, but improve your bias, decrease the bias. Most people believe the only way to do this is to complicate the algorithm, make it more complex, like a large decision tree. That would imply immediately decreasing the bias or the error, but it also implies overfitting, be more specific to data, so that's possible problems later.
Wouldn't aggregating simple things mean that those simple things would be related? Only then it would help.
So I think there was the several concerns. People have looked at ideas naively, though. In those 10 years, there was a naive belief that this cannot be done for reasons like they're too correlated. How can you learn more? On and on and on. But before we go into some of this stuff, let's do the simple things. Why would the variance going addition? We're going to call this an ensemble. And if you don't like this word, you can just call it a sum of simple things. Like, I'm putting simple things together, I'm adding them up. This is like regression, right? Regression takes your features, puts some coefficients on each one of them, and then adds them up. And then if you don't like to have all the features, use regularization like L1. And the stronger L1 is, the stronger say, I only want 20 features effectively. You put a larger L1, you put just 10 features, and so on and so forth. So regression is essentially, is not using a split, it's using a coefficient times the value, but in general it adds up, it adds things up. Why is the variance not a problem when I go that way, but it's definitely a problem when I go this way? So I think everybody can see how I overfit a tree if I go down. But why variance does not generally increase when I go adding things up? There's a law in mathematics, right? It talks about that. Somebody else? Yes.
Is it that the number of data points in that subtree remains like the same in different the same, and if you go like this, it reduces?
So I have the same data points. The data points don't change here, the same training set. I think we all know that if I start overfit, if I go down, we overfit, that means my learning outcome or model is very specific to that data set. And then that means high variance. That means if I choose a different training set, I'm going to end up with a different model and different predictions, right? That's what this variance means. If I change the training set and I redo the training, I end up with a different model that's so specific to that training set that when I run it on test or on production, I get different predictions. So variance means it's very specific to the training set. Why is it? So I'm hoping we'll understand what that happens when I go down, but why it doesn't happen when I keep adding things up? So what happens with the variance of a sum or an average or something like this?
You're not being specific when you are going, like adding different things. Those splits, if you see in terms of this, are going to be based on a different model possibly.
Right, possibly, but independent of how I generate, so I think he's concerned, he asked already two questions, and both questions are about the same thing, which is, how do you get the second guy? And once you have the second guy, how do you get the third guy and the fourth guy, right? I'm not there yet. I'm gonna have to figure this out. How do I get, but independent of how do I get the second tree or the third tree, or even the first tree, if I tell you I have 20 trees, somehow I got them. I trained them, I got them. And the prediction is a sum or an average. Sum or average means the same thing, right? Because if I need to divide by 20, I'm going to divide by 20. If everybody predicts a salary within the salary range, I have to divide by 20 at the end, right? Because it's like that magnitude plus that magnitude plus that magnitude, it's out of the salary range. I'll divide by 20 to get back in the range. So you can think about it as an average. 1 over the number times how many there are. Why is that good for variance?
When we are going down deep in a tree, we are making the output depend on more number of features. But when we are just adding small trees, each tree is depending on less number of features. So
Each tree, but overall, I could depend on the same number. If this tree uses 25 features, overall, I could still use 25 features, right? If I say this tree uses one feature, and another feature, and there's different features, that could be 25 features. So that's a good point, but the number of features being used, or thresholds, could be the same. Whatever somebody goes
but in a
down,
deep tree, the weights for each feature are decided based on each other. But if I have, say, 25 trees each using just one feature, the weight decided for that feature is independent of the other features.
weight is an informal thing here, right? I mean, what is weight? Like, we don't have weights in a decision tree. It's how many points go through that
Yeah.
path or something like this. He's getting warmer, but you need to cook it up. So I'm back to mathematical question. Why variance is not a problem when I add things? Assuming we all understand it's a problem when we go down, that becomes very specific. Yes.
As we go down, number of data points at each bucket decreases as we go down, but as we go to the right,
I have the
number
same
remains the
data
same.
points for every tree.
Yes.
That's I think what he wanted to say, but better words, better said it. As we go down, every split is determined by fewer and fewer data points, while in here, I still have all the data for all the trees. Of course, I need an algorithm to determine those trees. Yes.
Is this related to the central limit theorem?
Yes. So what is it?
If you have multiple models, then the mistakes are likely to average out and be close to the true prediction. Whereas if you have one model, it can overfit, there's no balancing factors.
So before we go that far, I actually wanted to go a lot closer to where we are. What happens to the variance in general? Just this recap math. Variance of a bunch of things, x1 plus x2 plus n divided by n. Variance of an average. What is that? How does that work? Variance of an average. I tell you, I have a bunch of random variables or predictors, and I want to compute a variance of their average. It's true that continuing this line of thought, you end up with central limit theorem. But before we go there, what is this? Yes.
In this case, like variance is basically deviation from the mean. So when we are dividing dividing the trees, like different trees, so the mean will be just, it won't be like deviating more from the mean because we are getting the mean based on just 2 points. When we are becoming more specific in down the tree, then we are like then the deviation can be like more from the mean of all those points. So like,
I don't say, maybe you're right. I'm looking for a very simple mathematical explanation here. There's a formula for variance assuming something, right? When you do variance of two things, what's variance of x1 plus x2? It's the variance of those guys,
Plus twice the covariance.
but when it's just that, when it's independent, right? So if it's independent, well, what happens if I average? Variance of x1 plus, still independent. So let's say x1 and x2 independent. Variance by 2, how that works? Is it the sum of the variances? x2 here, not x squared. Is it divided by 2?
Maybe 4.
That's what I'm asking. What is it? 2 or 4? or something else.
Or it's the variance of x1 divided by 2 plus variance of x2 divided by 2. When you pull the 2 out, you have to square it.
Uh-huh. So that's a 4. So how about for n? Assuming independence. What would this be? Variance of x1 plus variance of x n divided by
And square.
n squared. Now, can we see why this is decreasing the variance? Of course, assuming independence. If I have one thing that has variance something, 10, right? And then 10, and then 10. Let's assume, I'm just guessing that I have the same variance here. That's not true, of course, but let's just say 10, 10, 10, 10, 10. I sum up 20 of these guys. If I divide by 20, I get back to 10. But if I divide by 20 squared, I get a much lower variance. You should know this. Averaging stuff, any stuff, grades, salaries, people, performances, whatever. Averaging stuff decreases variance. Just general rule of nature. If you do one thing, you do a job, you make a bunch of money, right? And it's a variance. You're a contractor. You don't know how much money you're going to make for a job until you actually do the job, because the estimate doesn't match the work that you have to do sometimes, right? So the contractors have an estimate, I'm going to make on average $30 an hour, right? The truth is, when you do a job, you may get far off for that $30. Maybe you make more, maybe you make less. But if you do 100 jobs and you average how much money you make per hour over 100 jobs, that's going to be a much lower variance estimator. So if your mean is $30 per hour, when you do one job, the variance of how much you make per hour could be $19, could be $45, could be whatever. It's not unusual to get off the mean, right? But when you do 100 jobs, the average how much you make per hour, total divided by how many hours you work, that's going to be exactly $30. In other words, the variance of an average, it's much closer to zero, meaning the average is close to the mean. But one job could be far off. We can find so many examples like this. When you take a bus or a train, the average delay is 2 minutes. Well, when you take one bus or a train, that's gonna have sometimes early, sometimes late, could easily have 3 hours delay. But if you take the bus 100 times and you average the delays, that average is gonna be very close to the average delay.
So the last equation that we ended up in, is it ensemble one? Is it the decision tree one?
This one here,
Uh-huh.
this is gonna be the ensemble.
Ensemble. So we need to make the variance minimum as much as possible.
We don't want to concentrate on the variance. I'm saying that's going to happen due to this math formula.
And that's what we want.
Yeah, but that's not going to be our objective.
Mm.
Because if I'm claiming if we add up trees, variance is going to decrease by itself. We don't need to worry about that. The more we add things that are simple, what we should worry about is simplicity. We don't want any one of those to start having high variance. If every one of them is low variance, when I average them out, I'm not going to have a high variance. Assuming, of course, independence. Now, independence is not going to happen. It never does, right? But it's not that far off. Like you see in this naive Bayes, the fact that you're going to get a high performance on naive Bayes doesn't mean necessarily the data is independent. No, but naive Bayes works nevertheless. Same thing in here. I'm not going to have this guarantee of independence between my trees. I'm not even going to worry about. But I'm going to say, look, unless they are very, very dependent or related, right? If this variable would be the same exact variable, that'd be super correlated, right? What's going to happen if all these x's are the same x? How much is x plus x plus x plus x n time divided by n? X. Did I decrease the variance at all? No. That averages at least keeps the same variance that I started with, right? So at the minimum, even if it's super correlated, it does not increase the variance. But in practice, almost always going to be decreased. When you average things, even if they're correlated, you're going to decrease the variance. Now, do you believe me in here? When I average things, variance is going to decrease. It depends on independence. If the more independent things you average, the more you're going to decrease the variance. But at the minimum, theoretical guarantee is that this is not going to increase.
So when we say independence here, do we mean independence of features?
I mean, those trees have to do different things. I didn't specify that exactly.
Oh, sorry.
Right? But again, I'm not going to worry about it. My worry is to not massively increase the variance. And that's not going to happen for sure, even if the trees are correlated. The problem with the decision tree is that as you go down, you increase the variance a lot, meaning you make it very specific for data, meaning if tomorrow I have a different training set, I'm going to end up with totally different predictions. That's where the high variance comes into play. So what I'm saying here, doing this, it's probably going to decrease the variance even if I do crazy things, right? I didn't yet specify what those trees are. I'm just saying any trees we have. I'm not going to increase the variance, probably is going to get decreased. Hold on, what should I focus on? I want to ignore the variance. That's just a discussion to say variance not going to increase no matter what I do. Probably is going to decrease anything I do. This is fixed. This is just data. So what should I focus on when I design those trees? My algorithm for figuring out those trees now. Because what I've said so far, it's good for any trees, even random trees. But of course, I have an objective here, which is what? Yes.
Minimize NSE.
Which is the bias. Because this is fixed, nothing I can do. This is going to decrease if I average a bunch of things. Almost sure. I don't have to worry about it, even if I average random things. This is what I need to focus on. So I need somehow to take a weak predictor, sum up a bunch of them, and make it a strong prediction. So what I want to do is, now that I know the variance is not going to increase, I'm not going to overfit, or I'm not going to overfit that badly, what I need to do is to take a weak predictor that has like 60% accuracy, sum up a bunch of them, and get that to 90% accuracy, or something high. Is that possible? Now I'm going back to my comment early on. People were pretty convinced this is not possible. They even tried to prove it.
This looks something like what we did for gradient descent, in a way. Let's say you have a small data set. What you do is go on doing epochs on that again and again. So if you see it in this way, it's like you do one run of that, you do another run of that, like, you know, an epoch.
But I don't think the overall result was a sum of things. You're right, the weights, the coefficients were a result of a sequence of updates. But the overall predictor was a sum because of the regression function. Yes?
Do you have like a threshold of prediction on these simple trees? And like just run a bunch of different thresholds until you find the best ones and like delete the ones that perform worse?
You decide, you're talking about how to get those trees.
Yeah.
So people have tried that. If I generate a bunch of random trees, or not so random, I select the ones that do reasonably well, independently. How many trees do I need? If I get a bunch of trees, like I ask every one of you to produce a tree, a simple tree, it's gonna be 60-something%, right? And then I keep the best 10 trees. When I average, can I say I improve the average? I'm gonna decrease the variance, right? The fact that I average 10 trees, my variance of the prediction is gonna decrease. That's good. But can I increase the bias, the performance that way by picking 10 random trees and summing them up together?
No.
No. That's why people were so convinced this is not possible. Until somebody, which is now very, very famous, said, no, it is possible. That was his PhD thesis, and he won like the award for the best PhD thesis in the world for it. How to take a bunch of weak things, average them to get a strong machine learning algorithm. So this guy is now a professor at Princeton, Robert Shapiro, and he invented something complicated. And it took about 10 years for people to realize that his main claim is true. You can take a few things and average them together and make it good. But the way to do it, the way he did it, is not the right way. It could be done much simpler than that. So I'm going to tell you how he thought about it, and then eventually we're going to do the real simple thing. So here's how he thought about it.
Is this the David Boost paper?
Yes. So we're going to talk a little bit about AdaBoost, including some proof of why it works, why you can really decrease the bias. But then we say, okay, if you want to implement this for real, how would you do it? How is it done in practice right now? People don't implement AdaBoost anymore.
Can I ask a question?
Sure.
So we say that variance decreases as we go down in the buckets, but so-
Variance increases.
Sorry. So in the topmost bucket, we have the same data points, and in the leaves, we have the same data points, except they are splitted. So if the data points are the same, how variance are different from the topmost row to the buckets?
Well, we don't have an exact notion of variance here. This is the variance of the predicted as function of the training set. That is, if you use a different training set, you get different predictions. What I'm saying is every one of these cells becomes so specific
Yes.
that it's hard to generalize to other points.
Hmm.
So this is an informal, if your problem is that I didn't specify exactly what it means, that's why I posted as a problem. I want somebody to figure out, okay, what is this mathematically, what is this, and what is this, to get the square error. By the way, this is a very important equation for calibrators, for taking a bunch of predictions, not even machine learning, some scores, and calibrate them or normalize it with a specific purpose. Make probabilities look like real probabilities. Remember we talked about this, you do a sigmoid function, you get the fake probability. It's a number between 0 and 1, but it doesn't reflect probability of something happening. People, that's what they use in calibration. They decompose the error between truth and prediction, or some function that you have. They decompose it and say, there are 3 things here, and I want to minimize one of them more than the others. They have different names for it in statistics, sharpness, and granularity, things like that. But it's the same equation that tells you how accurate probability estimates are. So this equation appears in other contexts. The square error is the sum of 3 quantities: noise, accuracy, and dependency of specific data. Okay, let me move on so we don't get lost in the details here. So here's, let's see why is this possible. Here's an example. I have a 2-dimensional data. So this is my x1, that's my x2, 2 dimensions. And I have 10 data points. So here there are 3 pluses, 2 more pluses here, 3 minuses, and 1 minus here, and 1 minus here. And my classifier in here, the H is the weak learner, right? For simplicity, what is a split in 2 dimensions? What geometrically what a split means. You can pick one of the features and a threshold is there, right? So if I pick this feature and a threshold, what do I get geometrically? A vertical line. And if I pick this feature and threshold, what do I get? So that the weak learners are either horizontal line or vertical line. That's what the splits correspond to if you pick a feature threshold. Hands up, who's with me? Good. So what I can do here, I can pick a line and split the data into some side and the other side. I don't think there is a line that splits it very well. I mean, obviously, there's lines that do better than 50-50, but there's no line that does very well. That's exactly my point, that there's no line that's good. So let's assume, what's the best you can do in terms of errors with a line? So if I do this, this is line number 1. And I say the line number 1 splits in this being the plus side and this being the minus side. How many errors are in here? 3 errors? right? There's 1 minus here, that's an error, and 2 pluses here, that errors. Can you draw a line better than 3 errors?
Yeah.
Horizontal.
Vertical or horizontal, not diagonal. So that's the best line you can do. If you ask a decision tree do a split, there are other lines with 3 errors, but there's no line better than 3 errors. So the accuracy is 70% accuracy. Now again, any line that it's going to be either 70% or less. So there's no way to get better than 70%. Okay, so here's what now this guy idea was in 1995, for which he got so many prizes and became famous. If I look at the errors and I somehow make them more important, I say, this is the errors that I have, right? I ask the same algorithm, hey, give me another line, but I want you to somehow count these errors more now. So what I'm going to do, I'm going to have errors count more. So I want to focus somehow on what I've got wrong the first time. So now I have the same square, right? I have this plus, plus, plus here. The minuses is much bigger. This plus is much bigger, and this plus. Those are the errors. And these other ones are small. So I could say the non-errors count less. Somehow I already got this right. Somehow I don't need to focus on them. So now, of course, even though every line does 3 mistakes, the mistakes are not equal, right? The ones that are bigger count more, so I definitely want to get those right. And the mistakes I make is probably going to be some of the points that are not mistakes. So what happens here, can I draw a line like, I want to get this right, so how about this line in here?
This is good.
Let's get, I don't know, these pluses in here, this line. This is line number 2, this is the plus side, this is the minus side. No, that's not going to work because it gets this minus. Let's see, how do I draw a line? Oh no, that's correct, right? Sorry. 2 plus, 2 minus, right? It gets the 3 big points correct, but it still does 3 mistakes. We established from the beginning 3 mistakes are an upper bound. There's no way to do better than 3 mistakes, right? So what are the mistakes here?
3 pluses.
Those 3 pluses are mistakes now. So now if I repeat, this is round 3. But I somehow accumulate the errors. So I say, okay, in round 3, what happened? I have these pluses were mistake the first time, but not the second time, right? So these pluses are here. They were mistakes the first time, but not the second time. The same thing happened with this minus. And then I have these pluses, which were mistakes the second time, but not the first time, right? And all these points, what happened? At one round, they got more important when they were mistakes, and at one round, they got less important when were not mistakes, right? But what happened to the other points? So the other points are these 4 minuses.
Yes.
What happened to these 4 minuses?
They become much lesser.
They are both rounds, so they're correct both rounds, right? Both decision trees so far got them right. So those have the least important. And these ones, if every one of those points was 1 increase and 1 decrease. When it got incorrect, it was increased in importance. When it was correct, it was decreased in importance, right? So now if I ask the classifier, hey, you need to focus on the ones that are more important. All these were reasonably more important now than the minuses. Where's the classifier gonna go? To be honest with you, this was a minus here, right? Initially, so, yeah. So all those four, they were got correctly the first time and the second time, right? So they are the ones that have the least importance right now, and all of these are more important. Where my classifier is gonna go? Right here, right? That's line number 3. Which one is the plus side? Plus here, minus here, right? And then now, which are the mistakes? These ones are the mistakes now, right? This one is still correct. So this one, next round, will have the least importance because it got correct 3 times. And every one of those will be correct 2 times and incorrect once or something like that. So now, this is a classifier. Let's assume as a function it assigns 1 to plus and 0 to minus, or 1 and minus 1, something like that, right? This is another classifier. It assigns 1 and the minus 1, or 1 and 0. And this is another classifier, assigns 1 and minus 1, right? So is there a way to say my classifier will be some I can add some coefficients to these guys, right? I can add some weights if I want to. I have this lambda 1 h1 of x plus lambda 2, let me see, maybe the notes call it alpha. I want to, yeah, alpha. Well, h1 of x, it's really 1 and 0, right? Or 1 and minus 1. Again, h2 assigns 1 where? On this side, and 0 on that side. And what do I mean by this? Anywhere you look, you get a weighted average, right? For example, what's going to be this point right here? The first one assigns the first classifier. Negative. So let's take a point in here, right? Let's call this point x. What is this f of x going to be? Alpha 1, let's say this is, let's say it's a point A. h1 of A is?
Minus alpha 1.
Minus 1, right? h2 of A is?
Plus 1.
Alpha 2 of plus 1. And plus alpha 3 of h3 is?
Plus 1.
Plus 1. How about this point here? That's B. How is that going to work? Alpha 1 times plus 1 plus, it's a sign plus in that region. Alpha 2 times minus 1 plus alpha 3 plus 1. So my point is there some coefficients alpha 1, alpha 2, and alpha 3 that when you run all these 10 points, you get much better performance than 70%, right? We established any line we do is going to have 70% accuracy. But now we draw 3 lines. Is there some alpha 1, alpha 2, and alpha 3? Then when I put them here, every single one of these points gets the correct value.
Yeah,
Yep. Which ones are those?
I think 1, 1, and 1.
No.
Number of correct divided by total points.
This is 0.42, 0.65, and this alpha 3 is 0.92. So you can do it as an exercise, run those values, see what you get, and I'm telling you, every single point here will be classified. This is a very simple picture, right? It's this diagram here with 3 lines, with 3 numbers, and you only have to try for 10 points. This was a breakthrough idea. this example here proves that what everyone believes that there's no way to combine simple things to get you an accurate thing, it's actually not true. It doesn't tell you how to obtain the lines or how to compute the alphas, but clearly it's a counterexample of the statement, there's no way to combine few simple things to get an accurate thing, because I'm combining three 70% classifiers and I'm getting 100% classifier. So this will result in 100% accuracy for those 10 points. Okay, so when he noticed that, he's like, okay, how do I get those trees and the alphas? So I'm going to show you the algorithm. And then the algorithm, once somebody shows it to you, it's easy, but it took years of PhD grad school to figure out. Okay? But once I show it to you, it's not gonna, we'll do it in 20 minutes. So here's the idea. I'm gonna loop a bunch of rounds, epochs or rounds. And I'm going to say I have a distribution D. Hello? This is advertisement for electricity company. So epoch. It's T, let's call it T. Epoch 1, 2, 3, 4, right? T. There's a dt of any x importance of xi at epoch t. So obviously this is a distribution. Like sum over all I of dt of xi sums to 1. Initially, it's uniform because all data points count the same. So initially, d1 or d0, I forgot which one is here, d1 of x is uniform. So that's 1 over how many data points I have for every x. Right? Initially, I start. The first picture was everybody counts the same, so I draw a line of 3 arrows. What I want is a weak classifier, so I have to get a ht of x weak. So that's a training phase. Weak learner. You can really think of this way like simple decision trees. Like literally, I pick a feature a threshold, and a feature a threshold means one cut in the table. That's what it means, right? In the data space. Train with respect to that dt. So when I trade a learner, hey, I need a decision tree or a line or whatever it is, I need to train by taking into account that importance, right? I need to tell it at this round t, some data is more important. That's what I said here. And here I told it those 3 points are more important. And then later I said those 6 points are more important than the other 4. So when I tell it train, at every round, I'm going to say focus on this particular data points, right? So with respect to dt, that means my error, say epsilon t, is with respect to dt. The error is going to be what? Let's do accuracy. So accuracy, it's 1 for every time my ht of xi is different from. So I'm measuring error, right? yi. Every time I get a different prediction, I'm counting as a 1 error, but it's going to be multiplied with who? dt of. Right. In other words, everybody counts as an error if you get it wrong, but it counts not as a 1. If you have a high importance, it counts high. If you have a low importance, count low. So obviously, by optimizing this error, I'm going to focus on the points that count more. I can afford to get wrong the points that have low DTs if I get right the points that have high DTs, right? This is going to be 1 or 0. It's 1 when my classifier gets it right, 0 when it gets it wrong. In my case, every classifier will make 3 mistakes. But by playing with this DT, I can focus on which 3 mistakes to make.
Does the classifier itself output ones and zeros, or do you threshold the output?
Let's assume this is a binary problem with 1 and 0. So like I have plus or minus, right? And every classifier, my decision tree will produce a plus or minus.
So then
You could have them produce real values and then average those real values. But that's already happening with this coefficient. The coefficients are effectively the values you want to assign to, right? By saying alpha times h, I make that 1 and 0 into 0 and alpha 1. So what you want to do, let's keep it conceptually as the classifiers produce 0 and 1. But then, of course, when I add the coefficient, it's not 0, 1 anymore. It's 0 or alpha 1. Make sense?
So then you have an f of b is like some real number. You say, does h of x equal y?
H itself is 1 or 0, and y it's 1 or 0.
So how do you get h from f? If f is going to be like a real value, sum of alpha.
So if it's only at the end, during the training I don't have f. I only have h1 at round 1, h2 around 2, h3 around 3. And I have this d's, the distribution of weights, that allows me to focus on something. F, it's only at the end, the function that I use as a sum at the end. So in here, let's make that more specific. ht of any x belongs to 0, 1, and y of every x belongs to 0, 1. Let's do the simpler case, right? So it's a plus and minus problem. Every classifier predicts a plus or a minus, just like we did decision trees. And I can measure the error with respect to some importance vector, dt, that I get to change at every round, right? At the first round, dt was uniform. So d1 is 1 over n everywhere, here. When I moved on, in here, which were the bigger? This was bigger, 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 those 3. So this, like d2 were big, d2 big, d2 big, and the other 6, 7 points were smaller in d2. So this d changed. And then in here, I have this d3 big, d3 big, d3, 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 and the other 4 were small, right? This was the importance at this round. Hands up who's with me. Okay. What do I need to do next? This will come as magic, so Harry Potter, okay? We'll get to it later, but for now, let's finish the thing. I'm going to compute that coefficient. Anybody wants to take a guess? Somebody guessed it already? Number of big points divided by the total?
Number of correct ones divided by the total.
Somebody else want to make a try? What would be this coefficient? I'm saying there's very less hope to guess this one because the guy who's very smart and now famous took 4 years to figure out who this alpha t is, right? So let me see if this makes any sense to you. Natural logarithm of 1 minus epsilon t divided by epsilon t. So-called the log of odds. As I said, I know it's magic. Trust me for a while, and then this is going to become clear what it is. And then what's the last thing I have to do? I've got my classifier for that round, right? H. I've got my coefficient for that round, alpha. That maps the 0 to 0, but the 1 into 0.65 or 0.92 or something. We can also make an observation here. Is the coefficient going to be, how is going to be depending on the error? If you have a small error, what this coefficient is going to be, small or high. So small error means close to 0. So 1 minus 0 divided by 0? High, that ends up high. Suppose now you have a very high error. So error close to 1. 1 minus 1 divided by 1? 0. Log of 0? Log of 0 is not defined, but as you go to 0, what happens to the logarithm? Very small, right? So this thing is going to end up small. What happens? So maybe 0 is a case that we need to deal with later. What happens when the error is 50%? That corresponds to common sense what? How do I get the 50% classifier? Random toss of the coin, right? So suppose epsilon is really 50%. I get a random classifier. 1 minus 50% divided by 50%? How much is it? 1. Log of 1? So when is this coefficient 0? When you get a random classifier. When it's very high? Super accurate classifier. And when it's negative, very negative, when your classifier is backwards, right? It's actually having a lot of error means what? You actually predicting backwards. So if you reverse it in a binary case that only works in binary, you actually get a very accurate classifier. So in that sense, alpha could help a lot to say, hey, if you have a very, very bad classifier, something that has 3% accuracy, that actually can help you a lot. Because alpha is going to reverse the sign. It's still going to give it a huge weight, but it's going to say, your H2 has a 3% accuracy. I'm going to give it a minus huge weight, minus 1,000. Is that going to work? It's going to work. Because instead of assigning 1, 0, now that thing assigns backwards 0, 1, or 1 and minus 1. And the weight tells it that's a very good classifier, because you just have to reverse it to have 97% accuracy now.
Yeah, but this works only for binary cases. Right?
True. That's true. But binary can do a lot of things. If you study multi-class problems, for example,
Yeah.
you can still binarize it, do each one. If you get binary super accurate classifier, you can almost solve any problem by binarize it first. So it still be a huge step to improve binary classification. What do I need to do to move on to the next round? So I got the classifier, I got the alpha, the error. Somebody
Assign
go.
weights to the point.
What?
Assign weights to the.
Recompute t plus 1, right? Okay, so this is the update dt plus 1 of xi is dt of xi, the old distribution. I'm going to do a multiplic update here. I'm going to say this is the same alpha, in case you wonder. If there are two kinds of points, right? The ones that this method, this last round gets correct, right? That's how I said. If it's correct, what happens to the weight? It decreases or increases? Correct points decrease, and incorrect points increase, right? Incorrect points, I need to focus on them more at the next round. So this is going to be if ht of xi, this is correct, right? And e at alpha t, if ht of xi is not yi, that is incorrect. But because of the shape of this thing, hold on, I'm going to write it again. E at minus alpha t here, E at alpha t here. That's multiplication with one of them, right? Of course, it's either correct or incorrect. So what is this? E at minus alpha t. Alpha t is a logarithm, so here that logarithm is the stuff inside. What happens to 1/2? Becomes square root. So it's the square root of 1 minus epsilon t divided by epsilon t. And if it's incorrect, I'm multiplying. This is a multiplication here, right? And it's one of them. It's either the, whichever it is. So this is going to be, well, hold on. There was a minus. So what happens to the minus? Flips what? So it's epsilon t divided by 1 minus epsilon t, and this one is 1 minus epsilon t divided by epsilon t. Clear, one is multiplying with some value, and the other one is dividing by that value, right? Because these are inverse to each other. Which one gonna be increasing here? So let's assume the error, since I'm training an algorithm, is going to be better than random, right? Let's assume the error is like I have in there 70%. Which one is going to increase and which one is going to decrease?
One minus epsilon upon epsilon will increase it.
Which one will increase? This increases or this increases?
The one.
This increases because the error is 30%. I get 70 divided by 30, that's more than 1. And this is 30 divided by 70, that's less than 1. So these incorrect ones are going to increase. That's what I want, right? The incorrect points have more importance next time. And I need to normalize this. I'm going to say ZT, that's normalization, to make it a distribution. So whatever those values are, they have to sum up to 1. So I can divide by their sum over all the data points to make it a distribution. Right? So it's a ZT here, that's what do I need to divide with. That's it. Right? That's called the Adamus algorithm. And at the very end, when I'm done, when I finish the loop, what's my classification function? What's my classifier when the loop is done? The classifier. It's written right there. F of x is
Linear combination of
sum of alpha I hi of x. And that has to be thresholded into, it's going to be a real value. If it's positive, I could be plus. If it's negative, I could be 0. So I can say thresholded at 0. Again, this was a breakthrough in 1994, 1995. Not so much the procedure, but it has theoretical advantages and simplicity. You can implement this, in fact you will, right away. It's simple, but it shows this very fundamental phenomena that you can combine in a simple way simple things and get the accurate classifier. And back to what we did before, that's not growing a tree, make it very, very specific to the training set. We already said that it's going to decrease the bias. That's what you guys did in homework 1. You grow the tree down enough, you're going to get 100% accuracy, right, with that tree. But the variance is super high. That tree is overfitting the data. So as soon as you change the training set, you get a different model. This is not increasing the variance. That was the original discussion today. It still decreases the bias a lot, but not at the expense of overfitting. That's a fundamental thing in machine learning. And not just the prizes this guy got and fame. It turns out just the test of time is the best in science. Test of time beats any prize like Nobel Prize or whatever. Because 100 years later, we know exactly what mattered from 100 years ago and what did not. Of course, we didn't pass 100 years because this was 1995. So how many years passed? 23 years, 24 years, let's say, maybe, right? We know that gradient boosting and boosting algorithms in general are still used in practice, in production. Of course, they're not the only things used, But there are so many cool ideas that got so many prizes over the years, none of them is in use for various reasons. This one still is. Random forests implements a boosting algorithm. And many problems are solved with gradient boosting. Not sometimes because it's better, sometimes because more robust, and sometimes because they're more interpretable. So just a quick parenthesis here. This versus neural networks, which are the two main algorithms used today for supervised classification. That is, when I have training data, I'm trying to learn from it. The main advantages of this method, as opposed to a neural network, which is the most popular today, is number one, much simpler to understand what it does. I can look at those trees with human eyes and figure out what's going on. So especially in processes where I need to justify the answer, it's not enough to produce a prediction, but a judge or somebody might ask, how did you produce that prediction, right? I have to explain it in a way that a judge or a doctor can understand how it was predicted. I cannot do that with a neural network. It's a gigantic mess that nobody can figure out. I mean, it does the right thing, but I can't explain the prediction. These, I can very easily produce the trees and the rules and say, here's why we produce that score or why it's high, because it has this split and that split and that split. We actually do this. Part of my consulting job is to take a learning algorithm and explaining to doctors when we make a prediction, if they want to see why you do it. Well, how do you explain it for non-machine learning people? You can't say, oh, it's a matrix multiplication, because they don't understand that. Right? You got to do something that people understand, because it has that word in the text. Right? The other huge advantage of this is it requires very little regularization hyper-tuning. In a neural network regression, you have to play with all these L1 and L2 regularizations. And unfortunately, the only way to do that with a theoretical guarantee is to train it multiple times. You choose your regularization penalty, train it, decrease it, train it again, increase it, train it again. It's like a binary search to check what's your best regularization policy. And it doesn't guarantee it's going to work for another data set. You have to hyper-regularize it, like try. People, when they run regression, they run 100 regressors with different hyperparameters just to see which one works. In here, we don't have to do that. We don't have to decide in advance. The main regularization parameter here, you want to take a guess what it is? Remember the thing that we're going to do? Right. The number of trees is the main regularization parameter. So we have alpha 1 times this, plus alpha 2 times that, plus alpha 3, plus alpha 4, right? What is the hyperparameter here? Trees are trees. We're going to train them with brute force, find the best threshold, find the best feature, and so on and so forth. Error is going to be measured with the given distribution. So in terms of hyperparameter, like I have to make a decision in advance, what do I have to decide? Number of trees. It turns out I don't have to train this thing 17 times with different number of trees. I can just train it once and decide when to stop. So I don't have to know in advance I'm going to have 100 trees, train it, then stop, start from scratch, train now with 20 trees, stop, start from the beginning, try with 30 trees. I can just keep training, and at some point I'll decide, stop it. So just one training. However, because decision trees are brute force by nature, remember, try all the features, try all the thresholds, that's going to be slower than one regressor, because regressor has this fast matrix multiplication, it works much faster. But if you train it an ensemble versus 100 regressors, that becomes pretty comparable depending what hardware you have.
How many trees do you usually end up with, and are there interpretability problems if you have too many?
They're not interpretability problems in general because only the high coefficient is going to matter, right? In terms of interpretability, even if I have 300 trees, most of the coefficients high will be like few trees. So you look at the top few trees, that's what's going to determine the outcome. Secondly, I think this, as compared to L1 regularization for regression that restricts the number of coefficients, it has to do with data. If you really need 300 features to do a good prediction, they're probably going to need to run 300 trees. So that's not uncommon to run 300 or 400 trees. Of course, as you keep going, the benefit of decreasing the bias, aka improving performance, it drops down, right? So initially there's high improvements per tree and then at the very end low improvements. I don't think you need to run more than a few hundred in general.
What is the lower bound of your weak learner so that the ensemble has to be great? Meaning,
Right. So that's a good question, not in the sense you're asking, but in a theoretical sense, which is we have a theorem that we actually have to prove. The proof is not required for you, but the theorem is. So I'm going to state the theorem here. It has to do exactly with this issue. Here's the theorem. So let me answer the question once I write the theorem down on the board. Ada boost, training error theorem. It says the training error is measured as probability with respect to the initial distribution D1 of f of x being different than y, right? This probability in practice is just 1 over n because it's uniform. D1, it's going to be uniform, right? I said the initial importance of data is 1 over n. Sum over an error for every time my f of x is different than y, right? Sum over all i's. That's what probability means in here. It's like how many of those you got wrong. Okay? So that is smaller than the product over all rounds, t equal 1 to big T. So I say loop for t equal 1 to some big T. I loop it like 300 rounds. I get 300 trees, right? Of 1 minus 4. I have it here. What is gamma squared? I don't want to introduce a different notation now. So gamma is a function of this epsilon. I'm going to put it here. Gamma t is, this is what I answer your questions, is how far away the error is from 50%. So his question is, what do I need to keep going in the sense of how accurate this classifiers needs to be? And if we look in here, we're going to prove the following, that we only need these classifiers to be a little tiny bit better than random. Just a tiny bit. 50.0001 will be enough. That has to be with respect, however, with whatever distribution is given to me, right? I mean, it's not 50% just initially. Just with any distribution I get over data points, this is what controls the importance. Who is more important at each round? I need this YT to be, this difference, I need to be bigger than 0.000001. I need this to be not random with a firm guarantee. Firm means it can't go slowly to 0. It's always that big. Okay.
Does this depend on independence between the trees?
No. But I'll get to that in a second.
so in this case, it should not. So in case of binary classifier, it should not be 50%. Because
It
you
should
get
not
that
be
inverted.
convergent to 60%. Because convergent means even though at some round it's 51%, it can go slowly down to 50%. See, this guarantees not convergent to 50%. So that error, and the absolute value really doesn't matter. We said we can flip a classifier, right? If somebody has 50% error of, 48%, sorry, 52% error, we just flip the classifier, we get a 48% classifier in the binary case, right? So we can say the error, we just say it's always less than 50%, but it can't reach 50%. So let me tell you why that is, assuming we can prove this thing. What does it mean? So I'm going to skip the proof. I'm going to do the proof next time. But what does this mean? If I can guarantee every single one of these guys, there's an inequality here that I'm going to put. This is pure math. It's, I think, this one in here. We don't need it, this one. Depends. My point in here that I want to do, it's easier to do it with this inequality, but even from here, we can say this converges when t goes to infinity. If I train enough rounds, t is the number of rounds, right? So as I keep going, where is this quantity going to end up? If those are not, so this, if these gamma t's are
M by t is 0.5.
is zero, if this is zero, what is this product of? Ones. But if it's not zero, if it's guaranteed to be a little bit of zero, this is a product of
Something less than
something less than one, and not just less than one, firmly less than one, right? Because if gamma is at least 0.001, gamma squared is at least something with many zeros and a one. Nevertheless, this is at most 0.99999. When I make a product of these guys, when t goes to infinity, what's going to happen with this? It's going to go to where?
zero.
The reason I'm putting this inequality is because some of you might be easier to see this in here. You don't need this part. But if you didn't understand how that goes to the square root, what's going to happen here? If these gammas are not zero, they're at least 0.01, their sum is going to go to sum of something that is not zero. It's guaranteed a little bit more than zero. What's the sum? The sum going to go to infinity when t goes to infinity. So then e at minus 2 times infinity goes to zero. Again, you can see that from here if you do the product of things that are a little bit less than 1, that goes to 0. Or you can see it from here. Either way, my point is the right side goes to 0, which means the left side must go to 0. Assuming I can guarantee this. Now in practice, this is easy to guarantee. All you need is a procedure that for any distribution of data produces a classifier better than 50% plus a little bit. You can't get close to, arbitrarily close to 50%. But this is usually easy to do. It's actually not easy to do if you go all the way to the end. If you do this for t goes to infinity, eventually that's how it's going to get stuck. Eventually boosting finds you a distribution for which there's no way to get better than 50%. But you're not going to train up to around 3 million. As I said, we're going to train few rounds of boosting, 100 rounds perhaps. In your data set, I don't think you need more than 50 rounds. And for the first 50 rounds, using a decision strategy, you're not going to run typically into this problem. So the moral of this theorem is that if gamma t is guaranteed to be bigger than 0.000001, then training error goes to, as t goes to infinity, training error goes to 0. What training error corresponds to in here? This is a guarantee of decreasing the bias. So the magic of this algorithm, besides the fact that it's super simple, it's not a fancy kernel support vector machine, right? It's a simple thing. Is that variance decrease happens for free. It's just averaging things. And the bias, you can see with a simple theoretical guarantee, simple as in, we're going to do the proof next time in class, it's not that big of a deal. You can see how, assuming you get this weak assumption of at least better than random by a little bit, overall when you sum them up, you decrease the bias, not just decrease it, you get it to 0. So this could achieve the same effect as overfitting right? Training zero accuracy when you do a decision tree, that's very big. You can achieve the same effect without increasing variance or overfitting. This has been a breakthrough in 1995. And when you're going to need to prove this theorem, whoever's talented at math and don't want to Google and all that can spend 2 days trying to prove this. It's not that hard. We're going to do the proof in class, okay? And then we're going to have to implement boosting algorithms. That is, you can tell from here it's not going to be a hard thing, right? This is going to be a distribution that's given. This is training your decision tree code from homework one split, except you're going to modify the error when you look for the split, say which split I need. You're going to account for this DT when you measure the error there. Because decision trees do brute force, try all split, see one choice better, but better has to be with respect to that distribution. This is nothing, just a quick calculation. This is nothing, just a quick calculation. Repeat for a few rounds, you're going to get high accuracy. Easy, right? This is not how it's done in practice, however. So I'm going to show you a variant of this which achieves roughly the same thing in a simpler way next time. All right. Oh, one more comment. I hope that's obvious. The weak classifiers don't have to be decision trees. The weak classifier HT can be any function that's simple and I can train it. I mean, you can plug in a neural network if you want. Theory will work exactly the same way if HT is a neural network. Because the training procedure is not part of this algorithm. Whatever you do to get that HT with respect to the distribution, it's an independent box from this algorithm.
So does that mean adding up a simple one layer neural network is better than going for a deeper?
It's better in some sense. It doesn't overfit that bad. But the neural network in itself, just one hidden neural network, is far more complex than a tree, so that can overfit by itself. People use decision trees here because they're more simple function possible. But you can use any function you want. Boosting, you can boost any learning algorithm. No, but that's fine, you still have to go and show the code. Maybe a misunderstanding. People who got grades